will end with solubility. Very important. The rule of thumb that's probably one of the most known rules in chemistry is like dissolves like, or compounds dissolve in solvents having similar kinds of intermolecular forces. Meaning that if you have polar compounds, they dissolve in polar solvents. If you have nonpolar or weakly polar compounds, they dissolve in nonpolar or weakly polar solvents. So a really, really famous example of this is, you all know, is that oil and water do not mix. You have oil and you have water. And the reason why they don't mix is because oil is made up of nonpolar molecules, and water is a polar molecule, or it's all polar molecules. So that's why they do not mix. They do not dissolve. So you see the two layers. You see a layer on the top, and then of course you see a layer on the bottom. So let's say this is a layer on the bottom, and again this is the layer on the top. Now I'm going to write two important terms here that you need to remember. That the layer on the top and layer on the bottom corresponds also to density. So the layer on the top would be less dense, and the layer on the bottom would be more dense. Now, generally, these two layers can be the aqueous layer and the organic layer. Generally, most of the time, the aqueous layer would be on the bottom because it's more dense, but I said not all the time, so generally. And the top layer would be called the organic layer. You're going to see that in the experiment. So how do we determine the solubility here? So there are some guidelines here. Is that most organic compounds are soluble in organic solvents. Okay, so organic solvents, again, like dissolves like. An organic compound is water soluble only if it contains one polar functional group capable of hydrogen bonding with the solvent for every 5 carbon atoms. This is very, very important. What am I supposed to say here? Well, what I'm saying is you can't just simply, have an alkane that's this long, and just because you have an OH on the bottom, you can say, oh, that's soluble in water. So that would not be soluble in water, because it's, again, just a huge, huge molecule that's made up of a long skeletal carbon skeleton that is nonpolar. So that's not the case. So here's how we would compare it. So ethanol right here is soluble in water. Because it has right here the OH. Again, this is capable of H bonding, and it's also a polar molecule. And it's a polar molecule. You only have 2 carbons here. We said for every 5 carbon atoms. However, when we go to the next one, you'll notice that it has, if you count these, you have 1, 2, 3, 4, 5, 6, right? So you have 1, 2, 3. This is actually 1. Let's see. 1, 2, 3, 4, 5, 6, 7. So these are 7 carbons here. And in this case, you have more than 5 for that OH right here. So in this case, you have a non-polar chain. Carbon chain. And this is simply too many. You have 7. Too many to be soluble in water. It could be soluble, but it's slightly soluble, very, very slightly soluble. However, what do you expect of butanol? Is that 5? So it has only 4 carbons in this case. So it should be soluble in water. And of course, this is also soluble in water. It has same number. In fact, this is actually more soluble because it minimizes the contact between the surface area of the carbons. Let's say if you have this molecule and another molecule. So that's the rule that goes here. Just to wrap up here some things is that there's a reason why cholesterol is not soluble in water versus ethanol. This is just way too big. All of it is non-polar chains here and rings, and you only have this H2O, this OH. So it's simply too large to be water soluble versus ethanol, which is soluble. Very well.